Determine the internal normal force, shear force, and bending moment acting at point C in the beam. To begin this problem, first of all, we need to convert our triangular distributed load into a point load for both of the triangles. When converting our leftmost triangle, we get our solution as 9 kilonewton, and so is for the other side because both are symmetrical. Now that we have that, we can find our external reaction forces, and we know our AX is going to be 0 because by inspection we know that there isn't any other horizontal force acting on it. Then we have AY and BY. And to solve for this problem, we can use either left or the right hand side from the C, and I'm going to use left hand side because it's easier. So all we have to do is take moment about the point B in order to determine our AY, and then we can start solving by method of section for our internal forces at point C. So moment about the point C, pardon me, B, gonna have counterclockwise 9 kilonewton, and it's 2 meters away. And then we have another 9, and it is 4 meters away from B. Finally, we have clockwise AY, and it's 6 meters away, and all of this is equal to 0. Solving for AY, we get our solution as 9 kilonewton. Now that we have our solution for AY, we can draw the free body diagram of the beam section at C. And as I said earlier, we're going to use leftmost side for C. So we're just going to have one external reaction force of 9 kilonewton. And then we're going to have our shear force at C, our normal force at C, and our moment at C. So we can first sum the forces in y direction in order to find our shear force. And before we do that, we'll have to determine our point load on this beam from the triangular distributed load we had earlier. So to find, first of all, we need to find the uniform distributed load value. So which is simply going to be, we're going to use proportionality. So we have 6 kilonewton, 3 meters equals to Rx, which is our proportionality for our force or the uniform distributed load, and divided by the distance to this point C, which is 1.5 meters. And solving for x, we get our value as 3 kilonewton per meter. Now we can sum the forces in y direction to get our solution. So we're going to have positive 9 kilonewton from AY, and then our point load is going to be negative because it's going downwards. It's going to be 0.5 times 3 times 1.5 meters. And then finally we have our shear, which is also negative. All of this is equal to 0. Solving for shear, we get our solution as 6.75 kilonewton. Now we can take moment about the point C in order to find our solution for moment at C. So we can have our unknown moment at C, and then we have our point load, which is counterclockwise, and it's 2.25 kilonewton, and it's going to be 0.5 meters away from C. And then we have AY, which is clockwise, and it's 1.5 meters away, all equals to 0. Solving for moment at C, we get our solution as positive 12.375 kilonewton per meter. Determine the internal normal force, shear force, and bending moment acting at point C in the beam. To solve this problem, first of all, we need to find our external reaction forces and our external pin connections. We're going to have AX, AY, DY, and DX. Because we just have to look for our internal forces at C, so we just need to find our external reaction forces at point A, in order to solve this, because we're going to take leftmost side or portion of this beam from point C. Now to find a solution for our horizontal reaction force at A, we can take moment about the point D. And we're going to have AX negative. It is tan 45 degrees times 3. And plus we have our point load converted from distributed load here, and it is going to be 30 kilonewton. And it is acting clockwise. So it's going to be negative, and AX is positive because it's counterclockwise. And it's 3 meters away from D, all equals to 0. All for AX, we get a solution as 30 kilonewton. Now we can find our solution for AY, and the best way is to isolate beam ABC or AB. Now let's draw its free body diagram first of all. So we're going to have our beam, point B in the middle somewhere, and then A. For A, we already have our AX, which is 30 kilonewton. And then AY, we still have to find. And our uniform distributed load. And before we even touch that, we have our horizontal and vertical reaction forces at B. And for our uniform distributed load, we're going to have two separate concentrated loads, one on each side of the B. Each will be 15 kilonewton. And now we can sum the forces, or even better, we can take the moment about the point B in order to find our solution for AY. We're going to have clockwise 15, 1.5 meters away, and then counterclockwise 15, 1.5 meters away. And then we have our clockwise AY, and it's 3 meters away, all equals to 0. So for AY, we get our solution as 0 kilonewton. Therefore, we know 0, 0. Now we can draw the free body diagram of the section till C. And as I said before, we're going to use leftmost side of the beam. So we have our cut here at C, and then our AY is 0, and our AX is 30 kilonewton. Now at C, we're going to have our shear force, a normal force, and a moment. Our normal force in this case is going to be simply 30 kilonewton, because by inspection we know that it will be 30 kilonewton because our AX is 30. And to find our shear, we have to first of all determine our point load here, which is simply going to be 5 times 1.5, which is 7.5 kilonewton. And because we don't even have to use an equation, we know our AY is 0, and by inspection we know our shear force is going to be negative 7.5 kilonewton. And finally our moment, for that we can use our moment equation. So all we have to do is take moment about the point C. We can have our unknown moment C. And then we have our counterclockwise 7.5 kilonewton, and it's 0.75 meters away. And all of this is equal to 0. Solving for our moment at C, we get a solution as negative 5.625 kilonewton. Now we can either keep these values as negative, or we could switch our vectors in our free body diagram and have them as positive. That's optional. And with that, we have our solution. For determine the internal normal force, shear force, and bending moment acting at point C in the beam. Solve this. Once again, we have to isolate this beam. That means we're just going to look at beam AB, and at AB we can have our external reaction forces, and at B we're just going to have our one vertical force reaction, and that's it. And now, before we proceed, we also need to determine our point load for our distributed load. So it's going to be 1350 pounds. Now we have that, we can find our external reaction forces, and thus we always look for the easiest ways to solve this, and in this case it's going to be right hand side, therefore we only need to find our reaction force for Py. So we can sum the moment at point A. In other words, we can take moment about the point A, and we have clockwise 800 pounds, and it's 3 feet away from A. Then we have 600 clockwise, and it's 6 feet away. Then we have our point load, which is clockwise, and it's 1350 pounds, and it is approximately 10.5 feet away. And finally we have our Py, which is counterclockwise, 15 feet away. All of this is equal to 0. Solving for Py, we get our solution as positive 1345 pounds. Now we can draw our free body diagram of the side we want to solve for, and we have already said that we're going to use right hand side. So we can have our By, which we found already, which is 1345 pounds. And then before we even look at C, we have to find our point load at this side of the beam, which is simply going to be 900 pounds. And now at C, we can have our shear, our normal force, and our moment. We can easily find our shear force, which is simply going to be when the force is in vertical direction. We're going to have positive shear, negative 900, then positive 1345 pounds, all equals to 0. Solving for shear, we get a solution as negative 445 pounds. And by inspection, we know that our normal force is going to be 0 pounds because there isn't any other horizontal force acting on this part of the beam. And then finally, a moment about the point C, simply summing the forces MC, or taking the moment about the point C, which is going to be just moment C, moment at C, and then we have clockwise 900 pounds, and it's 3 feet away. And then we have counterclockwise By, 6 feet away, all equals to 0. Solving for moment at C, we get a solution as 5370 pounds.